Hello and welcome to the presentation of the first group of the composite materials class, and we will be talking about composite tubes for small-scale structural reinforcement. By small-scale structural reinforcement, I mean, uh, well, for our example and purposes, or at least to what dictates our performance requirements, it would be a small balsa wing used on a small airplane, as you can see here. In this design, which we used for the 2020 AAA Design Build Fly competition, which we got second overall, uh, there's two carbon fiber spars that span the length of the wing, and this provides uh, rigidity just in case it would not bend or break with a lift that will carry the airplane. The motivation for this is that the carbon fiber tubes used in here cannot really be replaced by any traditional materials, as the whole wing is only 2 pounds of weight. So if you use a steel tube or even an aluminum tube, you don't want the structure to be majority just made out of the material, the reinforcement material, but rather you would want a more efficient material to deal with the weight savings. And of course, we run into cost problems, which will also be discussed later. Uh, Here we have a lineup of all the carbon fiber tubes used over the years. As you can see, there's two distinct types of them. From the top, you can see the first one consists of an inner protruded carbon fiber tube, which is reinforced by a filament winding with a 90-degree grain direction tube on the outside. If I recall correctly, this was used on a locking mechanism for a wing folding mechanism a few years ago. The second one, or actually the next three tubes, all have the same diameter, but you can see the different patterns. The first one is a filament winding with a fiber direction of 90 degrees. The second one is also a filament winding, but it is a layup of 90 and 0 degrees fibers that what I would assume to be a satin weave. The third one is a protruded carbon fiber tube. And for the last group, you can see they're square in shape, and this is a distinct ability of filament winding, which will also be talked about later. You can see both of these have a 0 and 90 degree layup. And another interesting ability for a square tube is better machining properties. As you can see, a hole is drilled. So for all of these tubes, what are the differences between a filament winding and a protrusion, and what are the costs, and what would ultimately serve the purpose of being able to replace traditional materials for a better structural reinforcement? We shall find out later.
The goal of the composite tube is to reinforce the aircraft wings under bending loads. From the diagram, we can see that lift is generating a counterclockwise bending moment about the root of the aircraft wing. The weight of the engine and the weight of the wing will generate a clockwise bending moment about the root. These bending moments may potentially lead to deformation and failure of the aircraft wing. In order to counteract this, a spar can be implemented to increase the wing's structural performance. An ideal spar would be something that is both stiff and light. If weight is not a critical consideration, then it could be made of any material that is stiff. However, for aeronautical applications, the material would have to be light enough for the aircraft to fly. Having lightweight parts can also decrease the running costs of the aircraft. Secondly, the spar would also have to be cheap to manufacture and needs to be manufactured at high volumes in a short amount of time in order to be applicable to commercial usage. Furthermore, it is important to note that when evaluating the effectiveness of a material, one should only consider what happens inside the elastic region, because once a part is bent, it cannot be used. Therefore, the spar should be made of protruded carbon fiber epoxy due to carbon fiber's high strength to weight ratio and the cheap processing costs of protrusion when manufacturing a high volume of composite tubes. Now let's take a look at what the advantages and disadvantages of protruded carbon fiber epoxy spars are when compared to its alternatives. Possible materials that could make a stiff spar include aluminum, low carbon steel, and fiberglass polyester. While steel is pretty stiff and is a pretty cheap material, an obvious disadvantage when compared to other potential materials is its heavy weight. On the other hand, aluminum is a much lighter material, but it is not as stiff as steel, and it is also more expensive than steel. There is also no point in having material that is heavier than the main material in which the wing is constructed out of, which is balsa wood in our case. Other materials to consider include fiberglass and carbon fiber, which are both much lighter than steel or aluminum. Fiberglass has a higher strength to weight ratio when compared to aluminum or steel. It is also cheaper than carbon fiber. However, carbon fiber is superior when it comes to its strength to weight ratio, making it the ideal material for the spar. Next, let's take a look at the different processing methods. Possible processing methods include filament winding and pultrusion. Filament winding would be ideal for forming complex shapes. There are also numerous layup options for filament winding. On the other hand, pultrusion is superior when it comes to fabricating parts with small diameters. Pultrusion is also more suitable for manufacturing at a high volume at a low price. It is also a common processing method to produce hollow structures with constant cross sections, such as tubes. Therefore, the preferred manufacturing method is protrusion.
The pultrusion process and the filament winding process can create very similar parts. Both processes require long fibers, but the orientation of these fibers vary. Fibers during the pultrusion process run parallel to the direction of the pultrusion. During the filament winding process, the fibers can be oriented in any direction. However, the direction in which fibers are oriented impacts how cracks will appear under stress. If the fibers run at 45 degrees, the cracks will be diagonal, as opposed to straight when they are oriented at 90 degrees. The pultrusion process has many fillers. Calcium carbonate can be added to lower cost. Aluminum trihydrate and antimony trioxide are used for fire retardancy, and aluminum silicate provides better insulation, opacity, surface finish, and chemical resistance. Both processes have unique winding structures, as the pultrusion process winding occurs in a longitudinal direction, and the filament winding can occur as hoop, helical, or polar winding. Each of them can create similar shapes. However, the pultrusion process can create tubes with smaller diameters, while the filament winding process can create non-circular tubes. The tolerance for both definitely varies on the products that are being created and the quality of the machinery being used. The tolerance for the pultrusion process often is very high due to the low pressure of the process, while tolerance for filament winding varies based on the mandrel, and high-end winders can have a tighter tolerance. Filament winding materials and pultrusion process materials have very different costs. Filament winding can cost $74 for 2 feet of material, while the pultrusion process can use materials at $16 for 2 feet. However, both processes cost a very high capital investment. With the pultrusion process, a die can be anywhere from $4,000 to $25,000. However, the lifespan of this die can be around 150,000 linear feet. On the other hand, a mandrel for the filament winding with a 48 to 60 inch steel long 1 to 2 diameter mandrel can cost between $50 to $100. However, a chrome plated mandrel can be between $250 and $500 with the same dimensions. With modest tooling, these processes can create consistent parts over time, which will lower the cost per product as product rates increase. However, it should be noted that both have a very high capital investment, with filament winding having a cheaper investment with higher material costs, and protrusion having higher capital investment with lower material costs.
The raw materials for the protrusion process are the combination of a reinforcement and a resin, the most common e-glass and unsaturated polyester. They usually use fabrics and mats as well to add bi- and multidirectional strength properties. Furthermore, protrusion involves some additives such as fillers, which improve insulation characteristics, chemical resistance, and lower costs, and calcium carbonates to further lower the cost and improve opacity. Filament winding consists of continuous fibers in yarns and liquid thermoset resins. The yarns are kept in spools and wet through a resin bath. Again, glass fibers are most common due to the low cost, while epoxy, polyester, and vinyl ester are used as resin materials. Moreover, glass fibers with polyester resins are widely used for low-cost applications. Prepreg tows are occasionally used as starting materials because they provide uniform fiber distribution and resin content throughout the thickness of the part. The pultrusion manufacturing process starts with spools of row wings being impregnated with resin. There are two impregnation options. The first is the open resin bath, which is the most common method due to its simplicity, while the second is injected resin, where reinforcement passes through a cavity where resin is injected under pressure. The problem with this second method is that it involves acquiring more expensive dyes. After impregnation, the fibers are passed through a heated dye which cures and solidifies the resin. The solidified material is pulled by caterpillar belts, pullers, or hydraulic clamp pullers. These pullers are mounted with rubber-coated pads that grip the composite material. The puller is distanced from the die in such a way that the composite material cools off enough to be gripped by the rubber pads. Some benefits for this material are the production of lowest cost composite parts due to its highly automated nature, as well as lower fiber and resin costs compared to prepregs and fabrics. Moreover, since it is a continuous process, this method allows for endless length of parts. However, these are cut to predetermined lengths using an automated saw or manual hacksaw. Some drawbacks are that this is a process which is limited to simple shapes, that is, tapered and complex shapes, and thin-walled parts cannot be produced, nor high-tolerance parts on the inside and outside dimensions. Filament winding involves placing a mandrel which has been coated with a release agent and a gel coat, and the gel coat is for high surface quality on the interior, on the filament winding machine. This mandrel rotates and the carriage unit moves relative to the mandrel to lay down the resin impregnated fibers at a specific angle. The carriage unit can move along the X, Y, and Z axes as well as rotate about these axes. Once the mandrel is prepared, it is placed between the head and tail stalks of the machine. When it comes to wet winding, fiber yarns are passed through the resin bath located in the carriage unit and then to the mandrel through the payout eye. Good fiber wet out and overall impregnation is important. This can be achieved by removing air held inside the fiber bundle and replacing it with resin, as well as keeping rovings at constant tension, which are passed through guided pins. Afterwards, the use of a doctor blade arrangement scrapes off excess resin and creates a uniform resin layer. A laminate is formed after a series of relative motion between the mandrel and the carriage unit. After creating the desired fiber angle distribution, the mandrel with the composite laminate is removed to a curing area where the laminate is cured at room temperature or at elevated temperatures. If thick parts are to be considered, it may be necessary to wind in stages and allow the laminate to cure between winding operations. Some benefits of the filament winding method are their specialty of creating tubular structures, which are the most common products made from this method. The method is attractive by utilizing low-cost raw material systems and low-cost tooling to make cost-effective composite parts. The process can be automated for the production of high-volume composite parts. Some drawbacks are its limitation to close and convex structured shapes. Not all fibers angles are easily produced during the filament winding process, and it is difficult to obtain uniform fiber distribution and resin content throughout the thickness of the part.
For the selected composite, we are targeting a low-cost market. Cost would be the driving factor here, but weight and mechanical properties are still very important. As previously stated, the primary purpose for these materials is for a wing sport, but they could also be used for hobbyists and for engineers to prototype larger scale designs. These composites should be good replacements for steel and aluminum at a higher cost, but still maintaining significantly better mechanical properties and a lower weight. The production methods we chose should make these composites easier to produce, allowing for cost savings and a better price for the end product. Overall, the aim of this project was to create a low-cost, high-performance composite to use in small-scale structural reinforcements. One of the main issues with using composites for structural reinforcements is the fact that manufacturing methods can be really expensive, especially when compared to those for metals. However, high-volume manufacturing methods like filament winding and pultrusion allow for a reduction of costs over time. Since cost was the main driver here, achieving a balance between mechanical properties and cost was essential. Therefore, pultrusion allows for the lowest costs, while filament winding allows for the best mechanical properties, albeit at a higher cost. Both methods, though, result in low costs relative to other carbon fiber composites while maintaining the necessary mechanical properties and weight savings necessary for our chosen applications. Therefore, in the end, our approach was successful in achieving the goal of producing a good composite tube for small-scale structural reinforcements.